Shell method is a technique for finding the volume of a 3D object by using definite integrals. Conceptually, it's similar to disk and ring methods that we learned in the last lectures, in the way that in shell method we also cut the object into infinitely many tiny pieces. After that, we find the volume of each piece, the differential volume, and then we integrate them all together to get the total volume. In disk and ring methods, we cut an object by using a flat plane, or you can call it a thin, sharp knife, to cut straight through, either horizontally or vertically. On the other hand, the shell method is a little bit different, as we are going to use thin, sharp tube to cut the object instead. Now, to further understand about this shell method, let's take a look at this illustration on the top left, this one. We have this blue curve, a parabola upside down, and the equation for this line is y equal to 3x minus x squared. I know that this curve actually continues down here, all the way down, but let's assume that it stops right here on x-axis. So we have the lower boundary of this region between the curve and the x-axis. And now we are going to revolve this region around this axis, shifted y-axis at x equal to minus 1. So x equal to minus 1 right here. So we are going to spin it around this straight vertical line along this direction. This blue region is going to show up on the left-hand side right here. Same shape. And now we get this green object that looks sort of like a donut cut in half horizontally with this red vertical line as the center. Once again, our goal is to find the volume of this object. And this time around, we are going to use thin, sharp tube to make the cut. Let's do that right here. Let's have a tube that is thin and sharp, sort of like a circular knife. Something like this. And this part is really sharp. And back here too, also sharp. And now we make a cut straight down on this green object. And now we get this cut on the green object. Let's take a look on the right hand side. This cut right here. And now we shrink this thin, sharp circular knife and then make a cut straight down again. And cut again. With that, we are going to get this cut right here, a little bit smaller than the first one. On the side too. And same at the base, a little bit smaller. And there you go, we have this slice of tube with some thickness right here. Also, let's make a note right here that this tube is hollow at the center. So in the middle, it's empty. At this point, I want you to focus on the thickness of this tube right here. Small distance from the inner shell to the outer shell. Also here on the left-hand side, from inner shell to outer shell. As you can see, these two small steps are two small steps in x direction. So this is dx, differential x. This one right here too. And just like in disk and ring method, when you see dx like this, differential x, you know right away that you are going to integrate on x variable. Now let's make a cut on this side along this line, straight down. and we take it down here on the left-hand side. This is the part that we just cut on this side and on this one too. So we have the same cut on the tube right here, and down here, and also here. And now we can see that the tube is unfolding. So let's expand it and make it flat. It should now look something like this on the right-hand side. It becomes a cuboid, a rectangular shape with some thickness. So thickness is right here, coming from the cut. So this is the cut that we just made. It's the same cut over here, and same right here, and also up here at the tube. They are all the same cut. Now back to the tube, let's assume that the volume of one slice of thin tube is equal to dV. And this means that the volume of the unfolding tube down here has to be dV too. Volume is dV. And same right here with the flat cuboid on the right-hand side. The volume of this piece is going to be equal to dV. By the way, let's make a note right here that this cuboid, rectangular shape with some thickness, is from unfolding tube. And now we want to find this differential volume, dV. And same right here, and this one right here, same thing. We want to know what dV is equal to. And dV is volume of one thin tube. Now let's move back to this flat cuboid right here. Since this is a cuboid, the volume is going to be equal to the height of this cuboid times the length of this cuboid times the thickness of this cuboid. So let's start with thickness. It's going to be this side on the flat cuboid, really small step, right here. And it's going to be the same side on the unfolding tube right here. Really small step. And in the end, it's going to be the same dx in the tube or the shell. Which means that this side right here is dx, and right here is also dx. And this means that the thickness of this flat cuboid is going to be dx. So let's put it right here, dx. And now the height is going to be this side on the cuboid. Same right here. This side on the unfolding tube or shell. And it's going to be the same right here. Okay, the height of the tube, and then it's going to be the same on the top left. This side. Straight down from the curve to the x-axis. As you can see, this height is the distance from x-axis to the curve. In other words, this is function value. So this height is going to be equal to the function value f of x, which is right here, equal to y. So the expression of the height in terms of x, the main variable, is right here, and it's equal to 3x minus x squared. So let's use it down here. The height of the shell is equal to function of x. F of x, in this case, is equal to 3x minus x squared. Let's make a note right here that this is the distance from x-axis to the curve. And now last one, the length of this volume, dV, is going to be this side on the flat cuboid. And it's going to be the same side over here, same line on the unfolding tube or shell. And this corresponds to this line over here on the tube. The inner circumference of this tube or shell, the inside circle along this line. And now we know that the length that we want to find is going to be equal to the formula for the circumference of a circle, and that is 2 pi r. And now we find this radius on the tube. It's going to be this line starting at this point at the center of the tube, and it goes out and stops at the inner surface right here, this arrow. This is the same arrow that we have over here on the left hand side, starting at the center of this object. On this axis, x equal to minus 1, and it goes out and stops at the inner surface of this object. Same arrow. Same radius, r. Let's make a note down here that the radius r in this case corresponds to horizontal distance from the center of this object to the curve. When you see this horizontal distance, you know right away that this is x value. So make a note right here. This is x value. Just x, not function value. This is different from this one down here, the height of the shell, because this one down here is vertical distance. So let's add right here. This one is vertical distance. And when you see this vertical distance, you know right away that this is y value. That's why we need to use f of x right here, because this is y value. Now back to the horizontal distance up here. It's x value, which means that r is going to be equal to just x. Not f of x, just x. However, in this case, the center axis is shifted to the left 1 unit to x equal to minus 1. It means that the radius is going to be longer by 1. So we need to add plus 1 right here because of the shifted center axis. And now we have the expression for the radius in terms of x. So this one is radius in terms of x. And now we know that the length down here is going to be equal to 2 pi r. And r is equal to x plus 1. Now let's use it right here. For the length of the shell, it's going to be equal to 2 pi r, the circumference of the inner surface. And in this case, it's going to be equal to 2 pi times x plus 1. Once again, let's make a note that this is horizontal distance from center to curve. And we have this plus 1 right here because shifted center axis at x equal to minus 1, shifted to the left 1 unit, and that's why the radius is longer by 1 unit. And right now we know the height, the length, and the thickness. Let's put everything together to find dv. The height is going to be equal to 3x minus x squared times the length, which is equal to 2 pi times x plus 1 times the thickness, which is dx. So first term is height. Second term, 2 pi x plus 1. This is length. And last one, thickness. And now we have the formula for dv. differential volume for one thin tube, or one thin shell if you want to call it that way. And now the total volume of this whole object, big V, is going to be equal to integral of dV, differential volume. So we are going to add the volumes of all these thin shells together. And in this case, it's going to be equal to definite integral of dV, which we know it's equal to this. So let's put everything in. 3x minus x squared times 2 pi times x plus 1 dx. And now we integrate from the starting point x equal to a to the end point x equal to b. And now we need to find a and b in this case, equal to what? Now back to the graph on the top left. We can see that the region starts at x equal to 0, right here. So this is a, and it ends at x equal to 3. So this point is b. So we know that in this case, a is equal to 0, and b is equal to 3. Now that we got all the informations, all we need to do is to evaluate this definite integral to find the total volume of this object. In this example, we want to find the volume of the object created by revolving a region around x-axis. With this around x-axis, we know right away that this object will have a symmetry. Around x-axis. Keep this in mind, it might be useful later. Now we take a look at this region on the right-hand side. So we have this blue curve, and the equation for this curve is right here. X equal to 12 times parenthesis of y squared minus y cubed. As you can see, this blue region is trapped between the curve and y-axis. And now we revolve this region around x-axis, spin it in this direction. And now we should get the same curve under x-axis looking like this. It's a duplicate of the curve that we have above x-axis. And now let's extend y-axis down here. This part, this region, is also filled, like what we have above. And now we have the opening or the mouth of this object on the right-hand side, looking like this. And the base on the left-hand side should be a little bit curvy. The center of this object is hollow, so empty here, while this part up here is filled. Also filled down here. Now that we have successfully plotted this 3D object, let's find the volume of this. What about in this example? We use shell method to find the volume of this object. And this means that we need to find cylindrical shell by using a thin, sharp, circular knife. So let's do that right here. Let's have a circular knife, something like this. Let's assume that this part is really sharp. And also back here. And now we cut horizontally in this direction on the object. And now we should get this cross section. And since this knife cuts all the way through horizontally, we should get this side and also down here. Cut all the way through. And now we shrink the knife and cut again. And now we get another cross section looking like this. Cut all the way through, from right to left, like this. And down here too. Cut all the way. At the base, we should have something like this. Since we have two cross sections, it means that this tube must have thickness right here. All the way around, in circular shape, a circle. And now we have a thin tube right here. Or you can call it a shell. And our job is to find the volume of this. Let's call it dV. Differential volume. From the last slide, we learned that this tube or shell can be cut, spread out flat, and then turned into a cuboid. So we can turn this cylindrical shell into a flat cuboid. And this means that this dV, differential volume, can be found by the volume of the cuboid, which is equal to the height of the cuboid times the length times thickness. What about we start with thickness? Let's find this on the tube. It's going to correspond to this side from the inner surface to the outer surface. Same down here, from inner surface to the outer surface. As you can see, these two are small steps in y direction, so let's call it differential y, dy. So we have dy right here, and also down here dy. A really small step in vertical direction, y direction. And down here we have dy too. When you see dy like this, you know right away that we are going to be doing all the calculations on y variable. So we are going to integrate on y. This also means that all functions that we have in the calculation must be in terms of y. In terms of y variable. This means that height down here has to be in terms of y, h of y. Same with the length, L in terms of y. Now let's move to the left hand side. Let's find height, h of y equal to what? Now let's move back to the shell. Let's take a look here. The height of the tube corresponds to this side. From the base of the tube, it goes all the way up to the top of the tube. So this side is the height of the tube, h of y. From this horizontal black line, we know that the height of the tube corresponds to a horizontal distance from y-axis to the curve. And the equation for the curve is x equal to 12 times y squared minus y cubed. When you see this horizontal distance, you know right away that this is about x value. So we want the x value on the curve in terms of y, which is right here. X in terms of y for this curve, which means that we can use this expression for the height h of y right away. So we have this h of y equal to 12 times y squared minus y cubed. Keep in mind that when it comes to horizontal distance, it's all about x value. And that's why we got it right here, x value. And now we need to find the length L of y equal to what? By now we know that the length of the cuboid corresponds to the inner circumference of the tube right here. All the way around in circle. And now we know that the length L of y is going to be equal to the formula for the circumference of a circle, and that is 2 pi r. Since this has to depend on y, a function of y, it means that the radius has to be a function of y too. Radius is different at different values of y, depending on the location. Now let's find out about this r of y. What is it equal to? It's going to correspond to this distance from x-axis. Radius of the tube from here, and it goes up and stops on the curve. There you go. This is radius of the tube, r of y. Let me highlight this a little bit more so that it's easier to see. From this, we know that the radius r of y corresponds to a vertical distance from x-axis to the curve. And once again, when you see vertical distance like this, you know right away that this is about y value. Vertical distance, right? It has to be y. So at this point, we know that r of y, the radius, is the y value on the curve in terms of y. So what is it equal to? Y in terms of y. So it's just y. If you want y in terms of y, you can use y right away. And now L of y is going to be equal to 2 pi y, just y. And now we have all the terms for dV, differential volume. First one, thickness, dy. Second one, height, h of y is equal to 12 times y squared minus y cubed. Length equal to 2 pi y. So we can put everything together that we have so far to find the total volume of this object, big V. It's going to be equal to integral of dV, differential volume. At this point, we know that dV is equal to the height times the length times thickness. The height h of y in this case is equal to 12 times y squared minus y cubed. Now times the length L of y, and we know it's equal to 2 pi y. And now the last one, thickness, and that is dy. So this is height, and this one is length, and last one, thickness. And now we have to integrate these terms with respect to y, dy right here. From the starting point, y equal to a, which we don't know yet, to the end point, y equal to b, which we don't know either. So let's find a and b on the graph. As you can see, the region starts right here at y equal to 0. So this is the starting point. This is a. And it ends at y equal to 1, the end point, which is b. So down here we know that the starting point is equal to 0 and the end point is 1. And now all we need to do is to evaluate this definite integral to get the answer that we wanted. So first of all, I'm going to take all the constants to outside the integral to make it easier for us to work on. So 12 right here, a constant, goes outside. Same right here, 2 pi, a constant, goes outside. And now we have 24 pi at the front. Integral of what is left, and that is y squared minus y cubed times y dy. Integrate this from the starting point 0 to the end point 1. This is also equal to, now this y goes in right here and right here. So we have the same 24 pi integral of y cubed minus y to the fourth. Integrate them with respect to y from the starting point 0 to the end point 1. Now let's continue on the right hand side. It's going to be equal to 24 pi, still the same. And now we need to find the antiderivatives of these terms, y cubed minus y to the fourth. And that's going to be equal to, first one, antiderivative of y cubed, we have y, power increases by 1, we have 4, divided by the same number down here, minus antiderivative of y to the fourth, and that is y to the power of 5, increases by 1 and divided by same number, 5 down here. Evaluated at two values, starting point 0 and the end point 1. Final step, 24 pi is still here. And now the end point goes in. 1 goes in right here and right here. So we have 1 divided by 4 minus 1 over 5. These two are evaluated at the end point. Minus, now the starting point 0 goes in. Right here and right here. As you can see, everything goes to 0. So we have 0 at the end. And this comes out to be equal to 6 pi over 5. And since this is the volume of an object, this has to be cubic unit. And that is the answer for this example.